Welcome to the lecture on preprocessing part 2. Part of the material presented in this lecture is taken from the following book, while transcription and interpretation errors are responsibility of the lecturer. This lecture introduces the following concepts: cause of dimensionality, dimensionality reduction, binarization and discretization, and finally variable transformation. In many cases, we have to analyze datasets characterized by a high number of attributes. For example, documents represent as word frequency, where words are from a vocabulary which easily contains tens of thousands of elements or attributes. Reducing the number of attributes has several advantages. First of all, many data mining algorithms work better if the dimensionality, number of attributes, is lower. Irrelevant attributes are removed while noise in data is reduced. A second advantage is that of interpretability. Interpretability of the developed model is increased because it depends on a lower number of attributes. Then we have graphical representation, because graphical representation of data is facilitated. And finally, we have that amount of time and memory required by data mining algorithms is reduced. Many types of data analysis become significantly harder as the dimensionality of the data increases. In particular, as dimensionality increases, the data becomes increasingly sparse in the space it occupies. Here we represent the graph of the so-called cost of dimensionality phenomena. On the x-axis we have the dimensionality of the data mining model we develop, and on the y-axis we have the performance the data mining model achieves on a given dataset. We can see from the graph that increasing the dimensionality of the data mining model results in increasing the performance of the data mining model, so the performance it achieves on a given dataset up to a maximum. Then, increasing further the dimensionality of the data mining model results in a decrease of the performance, so the performance achieved by the data mining model degrades. It is extremely important to point out that the cost of dimensionality is an extremely important phenomenon, and we always have to take into account when we develop data mining models. Some of the most common approaches for dimensionality reduction, particularly for continuous attributes, use techniques from linear algebra to project the data from a high-dimensional space into a lower-dimensional space. Principal component analysis, also known as PCA, finds new attributes, the so-called principal components, that are linear combinations of the original attributes, are orthogonal, so they are perpendicular to each other, and are such that to capture the maximum amount of variation in the data. We are usually asked to specify the number of principal components to retain or the percentage of variation we want to explain with a given principal component analysis. Singular value decomposition, also known as SVD, is another linear algebra technique that is related to PCA, and it is also commonly used for dimensionality reduction. We now focus to binarization. It may be useful to transform continuous and discrete attributes into one or more binary attributes. Such a procedure is called binarization. Assume you have a dataset where the value of the qualitative attribute named taste measures the customer's judgment of a new type of canned soup. In particular, we assume that the attribute taste can take the following values: awful, poor, okay, good, and great. And now we show how binarization can be applied to these attributes. In such a situation, we add the column integer value and we associate to each of the possible values of the attribute taste a given integer: awful with 0, poor with 1, okay with 2, good with 3, and great with 4. In particular, we associate to the 5, k is equal to 5 possible values that the variable the attribute taste can take on, 5 integer values in the interval from 0 to 4. So in general, we will have the interval ranging from 0 to k minus 1. If the attribute is ordinal, then the order must be maintained by the assignment we use. And finally, this transformation is required also if the attribute is represented by integers, in the case where such integers are not in the interval from 0 to k minus 1. Then we convert the 5 integers to a binary number using s digits, where the number of digits s is computed to be the upper rounding of the log of k in base 2. In particular, in our case, so for the taste attribute, we have that s is equal to 3. Thus, 3 binary attributes are required to represent an attribute which can take 5 integer values. We then introduce the following 3 binary attributes: x1, x2, and x3. And each value that the attribute taste can take on will be associated with a triplet for x1, x2, x3. However, it may be the case that only the presence of the value 1 for a binary attribute is relevant. For example, in market basket analysis, only items that are included in the customer's basket are important. In such a setting, it is then necessary to introduce one binary attribute for each value that the categorical attribute can take. In particular, in our case, we will introduce 5 binary attributes ranging from x1 up to x5. It is clear then each value of the categorical attribute is associated with the value 1 of exactly one of the considered binary attributes. For example, the value awful for the attribute taste is associated with the value 1 of the binary attribute 1, while all the other attributes are set to 0. Another extremely relevant tool of preprocessing is discretization. Typically, discretization is applied to attributes that are used in classification or association analysis. The best discretization depends on the algorithm being used, as well as other attributes to be considered. Furthermore, we have that typically the discretization of an attribute is considered in isolation. Assume that we have to discretize the value of the income attribute, which is a continuous attribute, and here we report some of the value it takes. The first step we have to make is to sort in increasing order of values the records according to the income attribute. Then we are left with 2 different questions. The first one is how many categories to have, and the second question is where to locate the split points of the discretization. Before answering the previous 2 questions, it is important to recognize that discretization can be unsupervised or supervised. In particular, with unsupervised discretization, we do not exploit any information except the values of the continuous attribute to be discretized. To clarify as unsupervised discretization works, we present the following example. we take into account the income attribute, whose values have been already sorted from the smallest to the greatest, and the first step is to find which are the extremes of these values of the income attribute, which in our case are the one that I'm showing now, so 10,985 up to 21,230. The second step consists of asking the user which is the number of intervals he wants to use. In this case, we assume that the user specified that the number of intervals must be equal to 3. Then we have to find which are the split points. So we have to make the decision of what will be the value of the two split points to be used to discretize the income attribute. In our case, using these two split points, we will obtain three intervals ranging from the minimum value up to the first split point, from the first split point up to the second split point, and then from the second split point up to the maximum of the values of the income attribute. Then the three intervals have the same width in our case. Indeed, we can easily compute this difference and divide by 3, obtaining 3,415, which is the amplitude of each one of these three attributes. In this case, we then speak of equal width unsupervised discretization. Equal width unsupervised discretization is not the only option. We can also use a different option. For example, we can select as a split point this value, which occurs after the first 4 values of the income attribute, and as a second split point this value, which occurs after 8 observations of the income attribute. In this case, then, the split points will be 14,678 and 16,500. In particular, then, the 3 intervals we will obtain range from the minimum up to the first split point, from the first split point to the second split point, and then from the second split point to the maximum of the income attribute values. In this case, we have that the 3 intervals have approximately the same frequency. The first interval contains 4 observations that are the 4 that I am evidencing now. The second interval contains again 4 observations, while the third interval contains 5 observations. In this case, we speak about equal frequency unsupervised discretization. Discretization can also be supervised. In particular, supervised discretization exploits additional information, typically from the class attribute, to discretize the continuous attribute. Supervised discretization places split points in such a way that some measure of purity of the resulting intervals is maximized. The purity measure is computed exploiting the class attribute. Entropy is typically the computed measure of purity for a given interval, and it is defined as follows. Entropy is equal to the negative of the summation ranging over all the intervals of the product of the probability that a given observation belongs to the kth interval times the logarithms of this probability in base 2. Entropy is associated with the height interval, and if it contains only records of a given class, then we have that EI is equal to 0, so we have the maximum of the purity, while if it contains equally often all classes, then we have that EI is a maximum, and so in this case we have the minimum degree of purity. It is clear that a discretization has a high quality in the case when it has the maximum purity. We remark that supervised discretization based on entropy aims to find the split points of the continuous attribute such that the overall entropy is minimized. In such a case, then purity will be maximized. In particular, supervised discretization based on entropy aims to maximize the following quantity, aims to maximize capital E, which is defined to be the summation ranging from 1 to k, so the number of intervals of the product of Wi times Ei, so times the corresponding entropy value. In particular, capital K represents the number of intervals, M represents the number of records, Mi is the number of records in interval I, so the number of records belonging to the ith interval, and Wi, which acts as a weight in this formula, is defined to be the ratio of Mi to M, so it represents the fraction of records of observation belonging to the ith interval. In particular, we have to say that the quantity E is nothing that a weighted combination, a weighted linear combination of the values of the entropy, and each value of entropy associated with a given interval is weighted by the frequency of the records belonging to the corresponding interval. We now focus the attention to the discretization of categorical attributes. Categorical attributes can sometimes have too many values. In such a case, if the categorical attribute is ordinal, then techniques similar to those for continuous attributes can be used to reduce the number of categories. However, if the categorical attribute is nominal, then other approaches are needed. Let us now take into account the customer calls database. In such a setting, your friend informs you that states attribute values are grouped into states category. Thus, you take the decision to create a new attribute that you name state_cat, whose value depends on the value of the state attribute. You make the decision to proceed as follows. The state_cat attribute is such that it takes value on a smaller set than state, so it can take less values. In particular, you make the decision that state_cat can take just the following four values: C1, C2, C3, and C4. Now we show how to apply discretization in the case of categorical attributes. First, we focus the attention on the state attribute. Then we add the new attribute state_cat, and we associate to each value of the state attribute that is considered to be similar. In this case, we have KS, KS, KS that are equal, and also NJ that is assumed for a priori knowledge to be similar to KS. We associate to all these values of the state attribute the same value for the new attribute state_cat. So C1 for all the records where these values are present. Then we associate the value C2 of state_cat to OH and to MA. We associate the value C4 to OK, MO, and WV, and we are almost done in this case. Then, in this case, it is clear that you exploited domain knowledge and generated the new attribute named state_cat. So you generated a new attribute state_cat whose values are associated according to a priori knowledge to the values of the state attribute. However, in such a situation, you are left with the following question to be answered. What to do when domain knowledge is not available? The answer to the previous question is as follows. Empirical approach can be used. Empirical approach such as grouping values together only if such grouping results in improved classification performance or achieves some other data mining objective. We conclude this lecture by introducing variable transformation. A variable transformation refers to a transformation that is applied to all the values of a variable. Two types of variable transformations are available. The first is the simple functions transformation. In this case, a simple mathematical function is applied to each value individually. In this case, we have some examples as logarithm, square root, trigonometric functions, and so on. However, in such a setting, we are left with two major questions. The first one is whether the order needs to be maintained or not. The second is, does the transformation apply to all values, especially negative values and zero? The second type of variable transformation is normalization or standardization. It transforms entire set of values to have a particular property. In particular, x has mean equal to mu and standard deviation equal to sigma. In this case, a typical variable transformation, which is called standardization, computes the transformed variable as z to be equal to x minus mu divided by sigma. This is the so-called standardized variable. In this case, we know that z will be a variable with mean equal to 0 and standard deviation equal to 1. This type of variable transformation is particularly useful, for example, in the case where some of different continuous attributes have to be computed, because this transformation avoids one or few attributes taking large values to dominate the new attribute defined to be the sum. The same applies to other possibilities to combine attributes. However, we know that estimators of mean and standard deviation are strongly affected by anomalous observation, the so-called outliers, so the standardization is often modified. Typical modifications to avoid this bias are to replace the mean with the median and to replace the standard deviation with the absolute standard deviation. However, it is worthwhile to mention that more sophisticated methods to treat the bias problem are described in the specialized literature.